decay. They decay isotopes that are radioactive decay. They decay by releasing small particles, and those particles tend to have a little mass. So one of the particles that is released is a beta particle. That tends to be an electron. The other one is a helium. We call that alpha. Yeah, I believe we call that alpha, but it's a helium particle. And then you have gamma. Gamma is just energy. It's difficult to represent gamma. People just put it as 0 something. And then you have a neutron. So you can lose these particles from a sample. So if we say that carbon-13 has undergone a beta decay, that means he lost this particle and the numbers are going to change. For example, let's assume carbon-13 underwent a beta decay. So this is your sample carbon-13. He's going to break apart to undergo a beta decay. What do you think I should put here?
Carbon.
No, we don't know the element yet because now the number of protons are changing, right? So if I have to balance my 6 on the left and this side, I have to balance the 6. What should be down here? Huh? 6? No, cannot be 6 because 6 plus minus 1 is 5. What number should be down here so that the numbers here matches this number right here? 7. 7 has to be down here for whichever element this is. Okay, so let's put a question mark. We'll determine what that element is based on the number of protons. We use the number of protons to determine the element from the periodic table. And then what number should be on top of this question mark element? What number should be here to balance the number on top? 13. The same 13. Now, if I am to determine what element this is, which number should I go by? 7 or 13?
7.
7, which is the number of protons. So I go to the periodic table and see after the beta decay what element was formed.
Nitrogen.
Nitrogen. You're going to have such questions in your final, don't know, 3, 4, whatever it is, but they're going to be there. So that's how you do it. You're going to look here, the atomic number, the element that has the matching atomic number is nitrogen. The smaller number in the box. The periodic table is always given in chemistry exams. So the question mark right there is indeed a nitrogen. So your carbon-13 has decayed, losing a beta particle, forming a new element. Sometimes the element stays if the number down here that did not change, the number of protons did not change, you are looking at the same element. For example, if this carbon was releasing a gamma particle, so to speak, then it's simply going to be the same thing, but it's going to have a star on it. Like we put a star here or here to say, hey, this has undergone some transformation, only that the numbers do not change. Okay? So that's the idea about radioactivity. This is showing you the other, we talked about the electromagnetic spectrum during emission. I'm not going to talk about that. Yeah, so we say that the helium will be represented by that, the beta particle, so we call this alpha decay. So we call this a beta decay. That one is going to be E naught -1, and then this one usually does not have numbers, it's just by himself. Undetectable energy. We said last time that you really don't want to stand in the way of gamma rays. Your cells are going to be damaged, and then we say someone has cancer. If we don't want to expose ourselves to X-ray, if you don't want to expose yourself to X-ray, how about gamma rays? Very dangerous. Okay. So let me see. think I've talked about. Only energy release. I told you gamma is high energy. So let's talk about applications. Of course, applications is gonna be in carbon dating, in medicine. There are so many applications, and currently you even have nuclear bombs. They use that. Remember those two? What were those two cities in Japan?
Hiroshima and Nagasaki.
Yeah. Anyway, this is just showing you how animals can die in many thousands of years back. Some they say it's sometimes millions, and then they get decomposed. Once they get decomposed, they're gonna be recycled in form of a plant. You've had people joking and say, "I hope in my next life that I'm gonna be an oak tree. I hope I'm gonna be a cabbage," because it has to be recycled. We are either recycled as plants or we are recycled as crude oil. So I don't know if you hope you're gonna be gasoline or premium. I hope to be premium in my next life. But still, even after being burnt, it's taken as CO2. The CO2 is taken back into the plants, and the plants become eaten by animals, and then the cycle goes round and round. And either way, we're gonna be recycled. There is an instrument that they use in military. There is an instrument they use in military, which is a Geiger counter. Yeah, Geiger. I really don't know how to say it. I don't know if it's German. Sounds German to me. You see that when they're moving, like there's one movie called the Hyena Road, the military movie. I recommend you watch it only if you are not sensitive to seeing action. It's full of action and very touching, very emotional. So they send someone ahead of them to check the road. Many military movies will be like that, especially those that are in the Arab areas. They're filmed in the Arab areas. They'll send one guy to go with a stick, go checking. Then when there's so many clicks, the guy stops, and then he'll be telling the people, go back, and then maybe a sniper will shoot that very spot to blow up whatever is IED, right? They call it IED, to blow it up. So the Geiger, I don't know much about military, but anyway, I have so many military guys in my family, so I hear stories and I watch movies with them. So the Geiger counter instrument is kind of the same thing that is used to detect IEDs, or even in a simple item as a plate. You'll see in the lab, some of these cheap plates we buy in Goodwill or in thrift stores, they have radioactive stuff. And you put them in the microwave, what you're telling the sample to do is to radiate. So you think you're eating your burger that you just warmed in your microwave, but you're eating radioactive material. Then with time, probably you have ulcers, or with time, if you're a guy, you cannot make anyone pregnant because those radioactive materials are affecting the reproductive system. Or with time, if you're a lady, your periods times change, or you cannot get pregnant, you get ectopic pregnancy, a lot of complications. So cheap is expensive, that's what I'm saying. So when you're buying these things, think of what is what is the content of that material, because it can be very devastating down the line. And to track where the problem started is difficult. Okay. Anyway, I'll show you an example in the lab. So this thing gives you a count, and it kind of tells you by value. The scale tells you, like, this is probably how much you have in here in terms of concentration. We'll see it in the lab. Now, if you have 100 grams of a sample and it decays to 50%, to 50 grams, okay? 50% is 50 grams of 100 grams of a sample. The time taken for the sample to decay or break apart from 100 to 50 grams is called what?
The half-life.
Half-life. Now, some of them, okay, the 50 is going to change to 25. The same half-life is a constant. The 25 is going to change to 12.5. 12.5 is going to change to 6.25. 6.25 to 3.125, and it keeps on splitting, and that tells you that it's usually difficult for us to get to 0, right? Because you keep on dividing. Matter is not created or destroyed. So the atom, by definition, is the smallest particle of an element that cannot be further broken apart. So we will never go with this tier house to 0. No, it's gonna go almost touching the x-axis or the y-axis. That kind of a graph in math, we call it an asymptote. So look at this graph. We are starting roughly here. The rate of decay is the number of radioactive atoms that emit nuclear radiation per second. So it's a rate. So if I'm starting roughly there, and it's going this way, and I want to get the half-life, since I cannot read the numbers on here accurately, I'll go into the curve, decaying curve, and pick a number that I can half easily. So for example, let's look for, which one is the best here? Let's look at 30,000. The half of that will be 15. So hit the curve and go down. We read that, and then this is half. That's tier half. So again, go across with the ruler, go down. So I can tell that this difference, which that could be maybe 0.3, and this is a 10, the difference there in time taken in minutes is about 7 minutes, if I'm not wrong. And it's gonna be constant. Let's say we took 20,000, half of that is 10,000. This could be somewhat 13, and that could be somewhat 6. Again, it's this difference right here. It's the same as that difference, and it's roughly 7 minutes. So t a half is constant. Today, our instrument broke. We used it last semester, and that thing was smoking like crazy. So I told Jerry, I'm not gonna use this thing again. It's too old for life. Buy another one. But they checked, the price was so high at the time we were looking. So what I'll give you the numbers to plot. You'll plot at home. Just make sure that your graph. Make sure that I thought I had. Didn't I bring my book here? No, you're gonna use the graph in your book, the manual. But I'd prepared numbers, but I've forgotten them in the office. I'll have to go grab them after this. So I'll give you data, and then the data you'll use to plot a graph using the graph paper in your book. Don't use Excel. Want to make sure that you know how to plot it manually, and make sure that you cover more than 70% of a page. So if this is your graph paper, you don't want your graph hanging down here. You don't want it hanging up there. Scale your X and Y axis to cover much of the paper, basically. Okay, and then plot. Choose one point that looks easier for you to work with. If it's 100 on the y-axis, you're gonna choose 150. Draw the lines across, touch the curve, go down. The difference right there will be the t a half. It should be a constant. Okay, so that's what we'll be looking for in that graph. So we have these that will check. There's a radioactive element called americium, which was firstly discovered in America. That's why it got that name. 241. It decays by emission to neptunium-237 with a half-life of 432.2 years. What this is saying is that the radioactive material in here, if we put it today, if it's new today if it's new today, how many years should we wait until it decomposes to half its,
432.
yeah, 432. So do you think we'll be waiting that long? No. It's those guys 430 years after that are going to do the math backward. Okay? All right, some materials have a very short half-life, 3 minutes. Those are very radioactive. 2 minutes, very radioactive. We would have milked a cow and then used that instrument today, you would have seen. Not an actual cow, there's a setup that we call a cow that we usually milk the radioactive material and then we run it for experiment. But like I said, the instrument is broken. 2 of them are broken. All right. You know what this is, right? Where do you see that? A smoke detector. Now it's your turn. What's the missing product from this reaction? You're starting with phosphorus 32, and it looks like it emitted a particle we don't know. In turn, it made a sulfur. Remember how I gave you the example of a carbon changing to nitrogen? So it's the same idea. This is what I was saying. You're going to get similar questions in your final. Please practice.
Is that D, beta? Beta? Or is it D?
No, this one is the beta. This is the alpha. And then this is the gamma. So in the final, I believe the first question that you'll get, I'm not set it yet, but usually I do it standard. The first question you'll get is finding the half-life from a graph, just reading it. And then within the final, you're going to see questions like this alongside other experiments. So are you saying the answer is B, or you're just asking?
Is it B?
Let's test and see. If I put 0 here, I put -1 here. The -1 is going to reduce the 16 to 15. That's good. And then up here, there's no change. Yes, it has to be a beta emission. That is the idea. That's a beta emission. You just need to make sure the numbers on top. Let's say we had 2 elements here. What will you do? You sum up the numbers on the left and then sum up the numbers on the right and make sure they match. Subtraction and addition. Simple subtraction, simple addition. Let's look at another one. Identify the element E. This time you're given the particle that was a beta particle that was released, but we don't know if we're going to still have a carbon or we're going to have something else. What do you think?
Nitrogen.
Okay, so I think here's 14 stays, and this one is going to be a 7. And because this is number of protons, and because this is number of protons, then that means that you have a nitrogen. Go with the smaller number. It's not always that these small numbers are down here. They can all be written up. The smaller number is what's going to tell you the atomic number, which is going to tell you the element from the periodic table, okay? So I would have as well put this 6 up, 14 down. It's the same thing. You're focusing on the smaller number to identify the element. That's the idea. Identify E. I think we call this a positron, if I'm not wrong. Identify E anyway. Nothing changed here, right? And this is gonna be 34. Now, which element is having 34?
SE?
SE, selenium. Is it one of the choices here? You go with a smaller number to know the identity of the element. And that's how you do it. So you see some examples here. Sometimes you can have multiple emissions. For example, you're looking at cesium-137 being converted to barium-137. And then it has a letter there, M, which means that guy is not done decaying. It's metastable. It's not done decaying. So take that guy and have him decay one more time. Your product goes through another decay. Then it's gonna give you something that is more stable. So this is now stable. It's the same thing. You notice that the numbers are the same, right? The numbers are the same, only that this one has finished the process. This one is still active with the M. Yeah. And that's what they're showing here. So this one is releasing a gamma. This is the metastable one. This is the M one, I believe. It's releasing energy to give you that. And the reason the numbers are not changing is because we know that the gamma release, energy release, has no change in the numbers. It's 0, 0. That's the idea.